Yeah. Oh, by the way, the mask remind me about the COVID-19 the situation. I mean, you know, like Taiwan COVID-19 cases, the number of cases are increasing recently. So I don't know if the school is going to change the rule, okay, for the course, okay. As I told you at the beginning of the class, I personally prefer regular lecture, okay, because I can see you face to face and you know, get more interaction if by all means possible. But if school will change the course to online courses, I will notify you guys, okay, in advance, okay, and most likely it's going to be, if we are going to switch to online, okay, most likely we are going to use what is that? The Zoom, okay, Zoom, because my lab purchased the Zoom license, okay, for online lecture, okay. It's way better than the Google Meets, okay, trust me. So just want you guys to be aware of that, okay. I don't know, I mean, when the school is going to change the rule, but just in case, okay, if that happens, I will send a message to E-class and notify you guys, okay? So, okay, so come back to what we just talked about, okay? So, previously, okay, we keep saying Delaunay graph, okay? Even though I may slip my tongue a few times, but I should, when I say Delaunay triangulation, I should have said Delaunay graph. But after we introduce this statement, 3 points Pi, Pj, Pk are vertices of the same face. Okay, and these 3 points will, there'll be circle that goes through these 3 points, and it contains no point in its interior. Okay, because it means like this Pi, Pj, Pk define a face, right? And if a face has 3 vertices, that means it's what? It's a triangle, right? It's a triangle, right? So with this statement, we can now say it's a Delaunay triangulation. Okay, previously we couldn't say that because we may end up, have more than 3 points on the circle. Okay, in that case, then what happens that, you will have like you may have a face that has more than 3 vertices, something like this one, something like this. But as I already said, we assume the points are in general position, right? So this is not going to be an issue. Okay, so we don't need to worry about this situation. Okay, so because of that, then we will end up having triangles in a Delaunay graph. We only have triangles in a Delaunay graph, so we can call that Delaunay triangulation. Okay. So now, okay, there are a couple of additional theorems that we need to talk about. Okay, and these theorems help us to establish the equivalence between the the optimal angle vector triangulation and the Delaunay triangulation. Okay. So first, let P be a set of points in a plane, and let T be a triangulation of P. Then T is a Delaunay triangulation of P if only if the second circle of any triangle of T does not contain a point of P in its interior. Okay, so first, this is, remember like if T is a Delaunay triangulation, then T satisfies this thing, right? Satisfy this, right? And because T satisfies this, you can see that the circle through Pi, Pj, Pk contains no point of P in its interior. So if it's Delaunay triangulation, then yeah, we have, if T is Delaunay triangulation, the second circle of any triangle of T does not contain any a point of P in its interior. I mean, this direction is obviously true, right? From left to right. Okay, it's obviously true. Okay, from right to left. Okay, if there's no, if T does not contain a point of P in its interior. Okay, for every triangle, there's I mean the circle, the second circle. Okay, 外接圆呐。Yeah, 外接圆. Okay, second circle that goes through those three, vertex of triangle contains no point in this circle. Well, that's exactly what happens in a Delaunay triangle, in a Voronoi diagram, right? That's a circle event. Remember, that's a circle event, and the circle event, I mean, is equivalent to the face in Delaunay triangulation, right? Which obviously is a triangle, right? So this if and only if is very easy to establish. Okay. The second one, okay, let P be a set of points in the plane. A triangulation T of P is legal if only if T is a Delaunay triangulation of P. Okay, so if T is Delaunay triangulation, okay, from this one to here, it's so obvious. Why? The second, this statement established the equivalence between the angle, the optimal angle vector triangulation and the Delaunay triangulation. This is a very important statement, okay? But from Delaunay triangulation to, I mean, P is legal. I mean, the triangulation is legal. Is very obvious. Why? Because, okay, say, how do we verify an edge is legal? I mean, okay, then it means like we have like say this is this point is outside of the circle, right? Okay, and this point is outside of the circle. And this point is outside of the circle, right? Right? For every triangle, right? Otherwise, you would have, conducted a edge flip, right? You would have conducted edge flip otherwise. So, okay, so in that case, that means, well, if it's Delaunay triangulation, I mean, you draw a circle, it contains no other sides inside it. So these 3 points must be outside of the circle, right? Right? So that means, okay, from this direction, if T is a Delaunay triangulation, this triangulation is legal. This direction is no problem, right? Okay. Here, of course, I'm using just one triangle, but it could be any triangle, right? It could be any triangle. So this direction is very easy to verify. The issue is the other direction. Okay. If a triangle is legal, okay, how do we know it is a Delaunay triangulation? What I mean is like this. Okay. I'm getting more and more certain that we wouldn't be able to finish most of the a lot of content in this chapter. Okay. Okay. Anyway. Okay. Say this is Pi, Pj, and the Pk. Okay, and you draw a circle. Oh, maybe I just use this one. Okay, Pi, Pj, Pk. Okay, you draw. We know. Okay, for a quadrilateral. Okay. Because this is legal, right? This is legal. It means that this point must be outside of this circle, right? Outside of this circle. Okay. Otherwise, it wouldn't be legal, right? Okay. But even we say that it doesn't exclude. It does not exclude the situation that we could have some additional point inside this circle. For example, like here. Right? We only say, for this quadrilateral, okay, when I say it's legal, I mean like you use three vertex and draw a circle. The fourth vertex is going to be outside of that circle, but I didn't say anything about the other point sites, right? So the other point site could appear inside this circle, right? Say PL. Okay. So now, okay, assume this is the case. Assume we have some sites that, assume the PIPJ, this is legal edge. We are proving this by contradiction. Okay, by contradiction. Okay, so first, we know, okay, for this quadrilateral, okay, we draw, for the circle that go past Pi, Pj, Pk, and this circle does not include Pm, but it includes some other sites. Okay, but it includes some other sites inside. Unfortunately, okay. Then, okay, let's assume. Okay, Okay. Let me see. PL. So we have some sites, and we select the PL. PL is the one that will maximize Yeah. PL, okay, it's going to maximize the, angle vector PI, PL, okay, and the PJ. This is the largest one. Okay, and remember that, okay, if you consider the PI, PJ, PL, and the PM for this quadrilateral, this is also a quadrilateral, right? Okay, this is also a quadrilateral. And when you draw a circle that go past PI, PJ, and the PM, obviously, okay, this circle is going to cover the, the original, this part of the circle in this part of this circle, right? So in other words, the PL will be inside of the circle, right? Okay, when you draw the circle that passes PI, PJ, PM, this circle will contain PL inside it, right? But, okay, we say this triangulation, all the edges are legal, right? So how can you have this one if, if this circle, okay, will contain this point inside, okay, for this quadrilateral, okay? So we have a contradiction, okay? So first, okay, if we have a point here, okay, that is inside this circle, okay, then using this circle and the original PM, then we know this point will be, this quadrilateral, okay, if you draw another circle that, yeah, let me see. Yeah, that go past PI, PJ, and the PM, okay, because you are trying to verify, okay, you already verify if this is, let me see, yeah, no, you are verify this one, okay, PM, PL, PJ, PM, PJ, you are verifying the PM, PJ if the PM, PJ is legal, because this circle pass PI, PJ, and the PM, right? Okay, and then, you know that, it shouldn't contain PL inside this circle. Okay, so we have a contradiction. Okay, so we have, if all the edges in P, all the edges in triangulation P is legal, then all the they are all triangulation, Delaunay triangulation. Okay, in other words, the circle shouldn't contain additional point inside it. Okay, otherwise we would have derived a contradiction. Okay, so this statement basically establishes the equivalence between the optimal angle vector triangulation and the Delaunay triangulation. And we have two other statements. Okay, first, let P be a set of points in the plane. Any angle optimal triangulation of P is a Delaunay triangulation. We obtained this one directly from the previous statement. Okay, because any angle optimal triangulation basically, any angle optimal triangulation means all the edges are legal, right? We talked about this earlier, right? Okay, and then any Delaunay triangulation of P makes the mean angle over all triangulations of P. This one, again, we obtain this one directly from the previous statement. So this is a given. Okay, the only thing that we need to prove is the second one. I mean, the other ones, I mean, we can sort of directly obtain the result from the proof. Okay, so now, well, we have a little bit more than 20 minutes. I guess I have time to talk about the algorithm, but I may not have time to talk about the complexity analysis. Okay, so let me talk about this algorithm. Okay, so obviously, as I said earlier, okay, we could have just used the Voronoi diagram algorithm, right? And then to compute the dual graph from the Voronoi diagram to obtain our Delaunay triangulation. That's not an issue. Okay, that's not an issue. Okay, we could do that. Okay, and it doesn't have an EO effect anyway. But here we are trying to talk about a brand new algorithm. Okay. So this algorithm, okay, unlike the Fortune's algorithm, okay, it's a Fortune's algorithm that compute the Voronoi diagram is a plane sweep algorithm, if you guys still remember, okay. But this Delaunay triangulation algorithm is a randomized incremental algorithm, okay. So because it's randomized, so its complexity is you could say it's easy to analyze, but later on we would probably not this week, but we will talk about that. I mean, probably next week. Okay, it's probably a little bit difficult to accept than you may originally think. Okay, but of course, because it's incremental, so we assume we start from a Delaunay triangulation first. Okay, so we start by inserting points one by one. Of course, it's a randomized process. So at the beginning, okay, it's like this. Okay, we pick 3 special points: P-2, P-1, and the P0. Okay, for these 3 points, P-2 and P-1 are additional points. They were not originally present in the point set. Okay? But the P0 represent the highest site. So among all the sites, we pick the highest site as P0. So P0 is, when you are given a set of points, P0 is fixed to be the one with the highest site. Okay? If you have more than one such highest site, you will use the one, rightmost one. Rightmost one. Okay? And what is P-2 and P-1? P-2 is higher than all the sites. And it is like, we assume it's like on the left-hand side, very far left of a horizontal line, which is higher than all the points. Okay, so P-2 can connect to P0. And all the points will be below it, will be below P-2 to P0. Okay, and the P-1 will be a special point. Again, it will be on a horizontal line below all the points. And P-1 will be the far right point. To be honest, the P-2 and P-1 does not necessarily need to be real point. We will do this symbolically. Okay? We will only do this P-2 and P-1 symbolically. Okay? So it's on the far left, upper left. P-1 is on the far lower right. And the purpose is so that P0, P-1, P-2, this triangle will include all the points inside this triangle. Okay? And then, okay, then we are going to insert the rest of points in random order. Okay? We will insert rest of point in random order. And because we start from this large triangle, right? Even though you feel like, oh, we have some points inside, so it's not a Voronoi diagram. It's not Delaunay triangulation, but it is a Delaunay triangulation. Why? Because at this moment, try to think only those 3 points. Try not to consider the point inside this triangle. Okay? So because you only have P0, P-1, P-2, so this triangle, even though it looks very narrow, okay, whatever you call it, because you only have three points, so you couldn't have any triangle. You couldn't have it has to be Delaunay triangulation, right? Because you only have these three points. Okay, so then, okay, when you start inserting point, okay, there are 2 cases that we need to consider. Okay, the first case, okay, assuming we already established the Delaunay triangulation to a certain point, okay, we already add P1, P2, P3, P4 up to PR minus 1. Okay, and we already maintain a Delaunay triangulation. Okay, and now we are adding PR. Okay, the PR, when you insert the PR, okay, the PR could appear inside a triangle, something like this, or it could happen that PR is on a line segment, right? Such as like it's on the line segment PIPJ. Okay, if it's inside a triangle, what happens is that it's going to break that triangle into 3 sub-triangles, right? And then each of these sub-triangles, okay, you need to consider, you may need to do a edge flip. Okay, you may need to do an edge flip. Okay, because this obviously has some neighbors, right? And because now you already break because you introduce this PR, so it breaks this triangle. Original this triangle before inserting PR, it's legal, right? It's legal. But now since you insert the PR, so you look at this triangle and the neighbor triangle, it may not be legal anymore. This line may not be legal anymore. So you need to, for each of the triangle, you need to do flip. And this effect may be propagated to the neighboring triangle. Okay, I will explain how it propagates later. Okay, same thing apply here. Okay, inserting PR to this case is going to break these 2 triangles into 4, right? And then, okay, you are going to check if this line segment is legal. If this line segment is legal, if this line segment is legal, if this line segment is legal. You have 4 segments to check. Okay, 4 line segments to check. So that's like the basic idea. Okay, so you can see that. Okay, first you can see here we compute random permutation of P1, P2 to Pn. Okay, of P, get rid of P0 because P0 we already use that. I mean, for the first triangle, right? The P0 will be the side with the highest y coordinate. Remember? So we get rid of that. And for the rest of the sides, for the rest of the points, we do a random permutations. And then from 1 to n, we try to find a triangle, Pi, Pj, Pk, okay, containing PR. If PR lies in the interior of the triangle, then it's the first case. Okay, so we are splitting this one, the Pi, Pj, Pk, into 3 triangles. And then remember, we have legalized edge. That's, we actually talk about, we actually talk about, not this one, not this one. Legalized edge is mentioned here. Okay, anyway, we'll talk about this quickly, shortly. Okay, so we need to call legalized edge for the 3, for this one, right? So that's why we have like we call legalized edge 3 times. For this one, we will call legalized edge 4 times. So for these 2 cases, either this case we call it 3 times. For this one, we call it 4 times. And then after we insert everything, okay, we are going to discard P-1, P-2 because those are additional sides, right? So we get rid of those sides. And all the incident edges for these 2 sides, we get rid of those things and then return the triangulations. Okay? And for legalized edge, okay, legalized edge, okay. So you can see if this one is illegal, what happens is that you first flip PIPJ. This one we already see that, okay. But this is a little bit different from the legalized triangulation. Okay, it is not a while loop. It is not a while loop. This is very important. You can see this is not a while loop, right? But of course, this is it is a recursive formula, recursive procedure. So you may still run into infinite loop, but it's not going to happen. It's not going to happen. Exactly the same reason as why legalized triangulation doesn't, the while loop doesn't run forever. Okay. So you flip this PIPJ to PRPK, and then you see you call legalized edge PR. So it's here. Okay. Let me use this one. Okay. If after inserting this point, okay, say this is like one of the triangles you just created is say this one, PI, this one. Okay, assume this is the thing here, PR, PI, PJ, right? This one. Okay, and this is the neighboring triangle. So you check if it's legal. If it's not legal, so you see, you are going to flip this edge to be this, right? And then what happens is that you need to further check PJ, PK, and the PK, PI, or PI, PK, PK, PJ. Okay, these 2 edges, because this one has its neighbor, this one has its neighbor. So you need to check if these 2 edges are legal or not. Okay, and if you keep looking at it, you will find that very interestingly. Okay, say if you insert a point here, okay, say originally this is a legal already Delaunay triangulation, and after the insertion, what happens is that it's going to, because you see, when you do the flip, okay, here, when you insert PR, look at here. The PR is going to be, it starts from 3 triangles that are incident to PR, right? But when you flip this one, you see you are going to have more triangles that are incident to PR, right? Okay, same thing, okay. At the beginning, you have 4 triangles that are incident to PR. And when you flip, let's say you flip this edge, okay, you are getting more triangles that they are incident to PR, right? Okay, so it's going to be something like so when you insert PR here, it's going to be something like this. Eventually, you are going to have a bunch of triangles that are incident to PR. And the fix will only happen locally. It doesn't, you can see, it only fix this area. It doesn't go beyond this shaded region. There's a certain local region that this fix is processed. Okay, the other part will not be affected. Okay. So this is like a very interesting observation. Okay. Then, okay. Here, okay. Every new edge created in Delaunay triangulation or in legalized edge during the insertion of PR is an edge of the Delaunay graph of P negative 2, P negative 1, P0, blah, blah, PR. So basically, like when you flip, so for example, here, when you flip this edge to this one, okay, you will see this edge stays. It stays. Okay. After the flip, that edge will stay. Okay. And as I say, you may flip this one, right? You may flip the top one, right? But you can see it doesn't change. This dotted line will not be affected anymore. And if you need to flip this edge, well, you will have another edge, right? You have another edge here, but that edge will stay as well. Okay, only the other edge that will be maybe affected, but not the one that is created because of the flip. Okay, that edge will stay. So that's what we are talking about here. Okay. The legalized edge during the insertion of PR is an edge of the Delaunay graph of this one. Okay, we call this one as we have notation, but I think where do we? Okay, we have set PR. Set PR. It means P negative 2, P negative 1, P0. Union P1, P2, to PR. This is capital P or capital PR. and we have DGR, Delaunay graph R. That means it's a Delaunay graph created by PR. Okay, just want you guys to be to understand. I mean the notation that we are going to use later. Okay. So there's one small question to answer that we haven't done that. Okay, we may need a little bit more time. Here, okay, you can see when we insert a point, okay, here, the statement number 7, find a triangle PI, PJ, PK containing PR. Well, how do we find it? We need to have an efficient manner to do this query, right? Given a point, okay, for the existing Delaunay triangulation, we need to find a triangle that that include this PR. So how do we do it? Okay, this is done. Remember the trapezoidal map example. Remember, trapezoidal map is also a randomized incremental algorithm. And in the trapezoidal map, we also need to find the point, the trapezoid that contains the point. The way we do it is we will construct a data structure that helps us to do the search, right? At the same time. So we are doing exactly like that. Okay? So we start from one single triangle, right? We start from one single triangle, and then blah, 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 and then we'll break it into multiple ones. But here, okay, let's assume, okay, to a certain point, we have 3 triangles. And then, okay, when you insert PR here, this insertion is going to break the delta 1, the first triangle, into 3, right? Okay, and then you are going to call the legalized edge for this edge and this edge and this edge, right? Okay, assuming these 2 are the boundary already. Okay, we assume these 2 are the boundary already. We don't need to flip them, but we need to flip this one. Okay, then what happens is that, okay, here. Okay, from the top, okay, you do the flipping, okay, to create delta 4 and delta 5. And one of them, this one, this very shallow triangle is gone. Okay, this one is gone. Okay, but when this triangle is gone, we don't delete it. Okay, we keep it, but we have a pointer that's point to the delta 4 and delta 5. Okay, and delta because this is the delta 4 and delta 5 were based on this one and the delta 2, right? So it's becoming something like this. Okay, and then we may need to do more edge flip. It turns out that delta 5 need to this edge need to flip. PK also need a flip. So what happens is that, okay, from here, okay, you can see we do one additional flip to create this one. So the delta 5 is gone, okay, and delta 3 is gone. So it's become from delta 5, delta 3, we create delta 6, delta 7. Okay, so basically, each edge flip is going to, add actually, each edge flip is going to add exactly 2 new triangles into this searchable data structure. Okay, this is a searchable data structure. Okay, so from top we can keep in mind that only the leaf leaf node, the bottom ones, are the current triangles. Okay, and you could easily search from the top to the bottom to find like which triangle contain this PR. Exactly the same way you search for which trapezoid contain a point in that particular trapezoidal map data structure. Okay. So this is something that you need to understand, okay, for the algorithm. In order to answer the statement 7, in order to do efficient like a query, okay, for that statement 7. So, well, we are running out of time. So I guess like we will stop here today, okay. Next time we'll start from here, okay. We will discuss like how do we treat P-1 and P-2 symbolically, okay. Yeah. Well, so any question?
How do we treat the next child during the search on that structure?
Yes, you need to compare with the age, the age that was flipped earlier. You will keep that age in the parent node. Okay. So here, okay. For example, let's say you want to search a point close to here. Okay. So what happens is that, okay, start from very beginning. Okay. This point is actually somewhere inside delta 3, right? Okay. So, well, you keep it in delta 3, right? And then, because delta 3 is now becoming delta 6 and delta 7, right? What delta 3 will store, it's going to store this line segment. And at that point, you're going to compare with this line segment to see if it's above or below. Okay, if it's above, then, if it's below, you are going to delta 7. If it's above, you go to delta 6. Okay, very good question, because we are going to talk about that later. Yeah, but in more detail, yes. Any other question? Okay, if no question, we will call it a day. Okay, thank you.